Well, hi, Dr. Flamo here, and welcome to the tape on timed exhaust systems, both the designing and construction of them. A timed exhaust system is one that pays attention to the firing order of the engine, and it will be built on a naturally aspirated racing engine that is raced up at Bonneville and the Dry Lakes, and it'll be raced in this Deuce Coupe right here. What is needed to build the system is just what exists in your own garage, the hand tools, and also some straight and U-bends from a muffler shop. And the way to actually connect the U-bends together, the technique of making both the curved sections and the straight sections, is covered in another Dr. Flamo tape called cross-ram induction manifolds. So now let's go back in time and see how this exhaust system was first designed and then built. And I have now got a lot of the other things that I need to get done. So now I get a chance to actually start building the timed exhaust system. And it is not really accepted theory on what I'm going to be trying to do. The accepted theory these days is equal length headers, or at least the runners coming down to the junction, and that's what everybody feels is the hot setup. But I have a disagreement with that, and my system will be unequal length tubing, and I'll show you why, or at least explain why. And that is that I'm trying to build this on the theory of drafting, such like the NASCARs do when they get into a train of cars where one is tucked in right behind the other and another one comes in, and you get about 4 or 5 cars all tucked in together, and each one is drafting the next one, and their efficiency goes up and their speed, of course, increases because of that. And when one car pulls out in the open to pass, they lose that drafting effect and they go in the wrong direction. So what I'm going to be trying to do is to design an exhaust system that does the same kind of drafting effect, where one slug of gas from one cylinder, when it joins into the tube with another one, will tuck in right behind it and draft, and then say a third one will come in and tuck right in and fit right behind the second one and continue to draft, and you make this train, like a NASCAR train, is going down through the exhaust system. Now, that's a lot of hand waving, but to really understand what that means, I've made a display that shows first a 4-cylinder engine and the way that train is formed of those exhaust slugs, and then we'll look at an equal length exhaust system on a modern V8 engine and see where that same system breaks down with a modern day V8. So here is the display. Okay, what you see here is a mock-up, or a display or mock-up of a 4-cylinder engine, and you can see the cylinders are right there. You can also probably tell that they're a Hemi engine, and I figure it's my mock-up, but I can have any engine I want, and I want a Hemi. So this is a 4-cylinder engine. It's cylinder 1, 2, 3, and 4. The motor's going in that direction. And the firing order there is 1, 3, 4, 2. That's the most popular firing order of a 4-cylinder engine. This simulates the equal length exhaust system where they come right down to this single tube. And what is wanted is that these exhaust slugs, as they come down here, they'll join one right behind the other and draft, just like I was talking about, with this sort of a NASCAR type train. Okay, now the lines that you see going across here are where we're going to be looking at the progress of these slugs every time the crankshaft rotates 90 degrees. So as these slugs come out, we'll look at them when the first slug stops at 90 degrees and then 180 and so forth, and we'll watch how they all progress. So now, since the firing order is 1, 3, 4, 2, all the mechanism for those cylinders, for those that are in that sequence, are going to be operating in exactly the same sequence. And since they're all balanced, they'll be firing at 180 degrees apart. So therefore you would expect the exhaust slug to come out of cylinder 1 and make it all the way down to 180 degrees before the next one that fires, which is number 3, and then its exhaust slug would start marching. So let's just see what this does. As the first cylinder fires and then the exhaust valve starts to open, out comes this slug of exhaust. When it reaches 90 degrees right there, nothing happens because this is a 4-cylinder motor and it's all firing at 180 degree sequences. So then it comes on down to 180 degrees, and when it reaches there, number 3 is now ready to discharge its exhaust slug. So it starts sliding out of the port, and then the next one would be 180 degrees later at 360 degrees, where number 4 in the sequence starts sending out its slug, and here it comes. And then they march on out until finally 540 degrees is reached, and that means number 2 cylinder is going to start sending out its exhaust slug. And so they all progress down here uniformly, and when they get to the collector, they all start lining up as soon as they get over the glue joint, like they do in a NASCAR train, and it operates like this. And then this guy tucks right in here and gets over the glue joint and right on out. And so this is what it looks like coming down the exhaust, and this is what you want, because every one is tucked in right behind the next one and drafting each other. Let's get this guy in the train here, and down it goes. Now that works fine for a 4-cylinder because every cylinder is firing 180 degrees from the next one in the firing sequence. The problem is with modern V8s that's not the case. So now let's go to a V8 engine. Okay, now we have a V8 engine, and you think it still looks the same, don't you? Well, this is just the left bank, the driver's side bank, and it has the same numbering systems that both Chrysler has and General Motors, and their numbering system goes 1, and then on the other side 2, and then back on the left side 3, and then on the right side 4, and so on. So on the left side we have cylinders 1, 3, 5, and 7. And since it's an 8-cylinder, there's the firing order that is both the same for Chrysler products and General Motors. And in fact, the sequence is the same for Ford also, but they use a different numbering system so it doesn't look like it is. But they're all operating with the same sequence. So now let's do the same thing with the modern V8, and we have a equal length header system coming down to the single tube on the left hand side. Well, first again, number 1 fires. There's number 1, and as it does, its first exhaust slug comes on out until 90 degrees. Now the next one fires is number 8. Well, that's on the other side, so this just continues right on down to the next 90 degrees. Now it's been out for 180 degrees, and number 4 fires, but that's still on the other side. So this progresses right on down to, 90, 180, 270 degrees, and then number 3 starts to exhaust. So out comes its exhaust, and then when we get to the next 90 degrees, number 6 fires. Well, that's on the other side. So then let's progress right on down to the next 90 degrees, and that would be number 5. So here comes number 5's exhaust, and then the next one that fires is number 7. And that's only 90 degrees away. So when this gets down to here, number 7 exhaust comes out because it's only 90 degrees from number 5. So when they progress on down, remember the first one that had the gap of 8 and 4 in between cylinders 1 and 3? That gap is right there. And so when this slug comes down and enters the tube, this one can't draft behind it, because this one has led by 90 degrees too much. Now these two guys were in the right sequence, which is number 3 and 5, but then look at this one that was only 90 degrees after this one started going, and it starts jamming up. So this one goes through the tube like that, but these guys are having a real distinct problem because they were only 90 degrees apart. So in the final situation, we have an area where this one could not draft behind this one, which lost efficiency. And then finally we have the collision between number 5 and 7 trying to get into the tube with only 90 degrees separation. And that is the problem with the V8 engine. So what has to be done is this cylinder has to be delayed so that it takes a longer time for number 1 cylinder to get into the tube, and that would shorten up the gap. This guy was in the right situation, but this one has to be delayed also so it backs up, and so that the whole train can then continue on out past the glue joint there and form that train that we need. But this one has to be delayed, and this one has to be delayed. And so now that is the next problem, is trying to figure out what length those have to be extended to delay these slugs, number 1 and number 7, so when they join together they fit in a nice sequence that we want going down the tube. So next is the calculations. Okay, so where do we start with the calculations? Well, we start trying to determine a distance, and that is the length that we have to increase those 2 outside pipes to delay those slugs 90 degrees of rotation of the crankshaft. Simple as that, okay? So actually, where do you start? Well, you start with trying to determine distance by using the old formula of velocity equals distance over time. Velocity, let's say, is 60 miles per hour. Okay? If you know 2 of those elements, you can figure out the third. So what we're going to be trying to do is determining both the velocity and the time that requires that slug to travel those 90 degrees of crankshaft rotation, and that will give us the distance. So first let's establish the velocity of that gas. Well, it's been pretty well established that the velocity gases run most efficiently between 200 and 300 feet per second. So if we shoot for right in the middle of the range, say 250 feet per second, we ought to have a pretty good shot at having it just right. So that's the first thing that's been established, is velocity. Now, the way to establish the actual velocity and make it real is by determining the size of the header pipes that are coming out of the head. If we make the pipes very narrow, it's going to squeeze the gases and accelerate them through the pipe at higher velocities. If we make them large, they're going to slow down and be lethargic, and the velocity will drop off. So we need to know what size diameter pipe to use coming off the headers to get the velocity up to and maintaining 250 feet per second. Well, that's also been established. And that's this chart that is right behind me. So let me zoom you in here, and we'll take a quick look. Okay, this chart, I'll get my wand out here, my scientific wand, and on this scale going up and down is the amount of cubic inches there is per cylinder. So I have a 240 or 250 cubic inch motor, and that works out to be around 31¼ cubic inches per cylinder. So I'm going to be looking at a zone right about here. If you had a 427, for instance, V8, and then the cylinders would be right around probably 53 cubic inches, and you'd be looking across the chart right across there. Okay? Now, when you go across this chart, you're going to see these lines that are coming down through here, and these are the lines for where you want your optimum RPM to be. And I'm going to be looking for around 6,000 RPM, so I am interested in this curve right here. Okay? And so the way this works is you go to whatever cubic inch your cylinder is, and you come across till you hit where let's say you want to run that engine at an optimum spot, and then when you come down, you will see that it says 1.7 inches diameter, and that is inside diameter of the tube. Now let's take an example here, and we're going to take my engine, because that's the one I want to build it for, and it's got about 31.25 cubic inches. So that line goes right across there. Okay, then I come down from that graph, right where it crosses 6,000 RPM, and when I come down, roughly, there it is. It says that the inside diameter for the pipe that I want to be able to maintain 250 feet per second velocity of the gases is right around 1.46 or 7. And that's just about the inside diameter of 1.5 OD exhaust pipe. So that's exactly what I'm going to be using off of each cylinder, is 1.5 OD, which is around 1.43 ID. So I don't know if you can see this, but if you can freeze frame this picture, then you can go to whatever cubic inch you've got and whatever RPM between 3,000, 4,000, 5,000, 6,000, and 7,000, and find out what diameter that you need to maintain that velocity. Okay, now let's go to the next step of figuring out the amount of time that's required to travel 90 degrees of rotation at 6,000 RPM. Stand by. Okay, so now in order to explain the time requirement, we need a new display. So here it is. That is what's known as a clean slate, and that's what we're going to use. So, the first thing that we have already now established is the velocity. So let's write that down here. The velocity equals 250 feet per second. Okay. Now, we're going to be dealing not in feet, but in inches. So in order to change that over to inches, that would equal this figure times 12, which turns out to be 3,000 inches per second. That's how fast the gas is traveling down the tube. Okay. Now, we've also got to change, we also have to deal with RPM, because we want one at 6,000 RPM. So the RPM we know to be 6,000. Okay. Now we would like to put that, this is revolutions per minute. We'd like to put it into seconds. That's the same thing we did with the feet. We went into inches. So let's bring this into seconds. So we're going to have to multiply, we're going to have to divide this by 60 to get how many revolutions per second. And when we do that, we get 100 revolutions per second. Okay, now we're cooking. Okay, let's just establish this a little bit better. That's not really written all that cool. I think I can do a little better. So 100 revolutions per second. If we have a full revolution, that's actually 4 90-degree segments, isn't it? So for every revolution, we sweep through 4 90-degree sectors. So we'll multiply this by 4 to get how many, this is how many 90-degree sectors per second at 6,000 RPM. Okay, now the next thing to do is to divide to find out how much of a second this is for each 90 degrees, because we only want to lengthen it one of these 90 degrees, not 400 of them. So now we take a second and we divide it by how many seconds, how many 90-degree segments there are in a second, and that means dividing 1 by 400. And now we find out that for every 90-degree revolution, we have 2.5 thousandths of a second per 90 degrees. That's how much of a second that crankshaft is spinning through a 90-degree sector at 6,000 RPM. Isn't this fun? Hey, let's move right along here. So now, we know from the very beginning that distance equals velocity times time. And so now we have both velocity, which is this, which we converted to that, and we have time, which is now this. So let's just go right ahead and use that information to write this equation this way. The distance, which is what we're actually going to want for a 90-degree segment, is equal to this 3,000 times this amount of time. Distance equals velocity times time. And when you multiply these two out, you find out that the distance that crankshaft, that tubing, that slug traveling at this speed has traveled every 90 degrees of rotation equals 7.5 inches at 6,000 RPM. And that is the amount of distance we have to extend the pipe to slow it down 90 degrees of a rotation of the crankshaft. Now, if you really don't like going through all this iteration for whatever one you're working on, you can condense this all down, and the distance is actually equal to the same thing when you do 45,000 over RPM. So if you don't like this, just use this thing. Once you've established the gas is traveling at 250 feet per second by using the right pipe diameter, then all you have to do is to take whatever RPM you want, plug it in here, and divide 45,000 with it, and you'll come out with exactly the right inches also. So this is now the equation, and we now know that this is the length that we have to extend those outside pipes. So now let's go on to the next phase, which will be design. Now when it comes to design of a timed exhaust system, there is probably none finer than the one that Lotus was doing back in the mid-60s. And here's an example of a Lotus 38 exhaust system that uses a Ford Cammer motor that won both Indy and the Grand Prix series back in those days, and driven by such notable drivers as Jimmy Clark and I believe Jackie Stewart. So let's take a look at this timed exhaust system and its design. Okay. I'm not suggesting that we make something as elaborate as something like this. This is a very exotic one, and yet it's almost like a beautiful piece of sculpture to me. If your tastes run along spaghetti lines. So, anyway, there's two things to note here. One of them is, here's the primary tubes that are coming along, and they are at different lengths. And when they come into the junction, they're in the theoretical world, you want to keep this exiting tube the same diameter as the entrance tube into the junction so that you can maintain the velocities. But in the real world, you're going to have some turbulence when this pipe dumps into this junction and then has to continue its journey on down that way. And so a good reasonable thing to do is to go ahead and expand the diameter of this tube only about 10 or 15% more than the primary tubes, because the gases will get jostled and they're going to slow down a bit. So instead of restricting them going into the same size tube, we expand the tube just a little bit larger. The other thing is that in order to conserve space, they made a 4-junction pipe coming into the 1 junction. And it obviously worked fine because they won both World Championships and Grand Prix and Indy with it. So the feeling is I really should go along with exactly that design. But there's one thing that troubles me, and I would like to depart from this design in one respect. And that is that imagine being inside this tube and you're a particle of gas jammed in this thing, and what keeps you from just going out in all directions is the containment of the tube. That holds you and forces you to go in one direction only, and that is out. So when you come down here, though, you come into a junction where the walls that contained you are now stripped away. There's a big door that opens up into this pipe, and when you come on down here, below you there's another door that opens up that actually goes back up this pipe, and directly across from you there's a big door that opens up into this back pipe. And then the whole floor drops away, and you're supposed to go right on down through here. But as you're going through this junction, after a while that slug gets jostled up, and the ones at the tail end are starting to feel a little pressure because they're trying to fit into this junction, and they're going to pick another avenue if there are 3 other doors that are open. See? So what I would like to do is I would like to contain this slug to maintain its velocity with as much containment as possible when I have a junction. And I can do that by having a junction of only 2 tubes rather than 4. So if you're now this particle coming down here, and here's the other tube coming down, when this particle gets to here, there's a big open door that you're supposed to go through, but there's only 1 door on the opposite side that you can sneak out of incorrectly, as opposed to this one that has 3 doors that you can incorrectly go. So that way the gas stays contained and will go down in a much better flowing velocity if it only has 1 door to seduce it into some other direction that you don't want it to go. And so what I'm going to be doing is building a tri-Y. And a tri-Y, imagine a tri-Y where the 2 center cylinders are timed, and they will just come into 1 Y junction and join right up. And the 2 cars will be in NASCAR style. Then on the ones that are lengthened, the 2 outside tubes, they'll have a second Y over here, and they'll join together in a nice NASCAR style. And then further on down from this tube and this tube, there'll be another Y that brings them both together, and the train will be complete at that point. And that is the design that I'd like to build. So now let's go into the actual construction of how those tubes are made to build these Y junctions. Okay, what I have done is I have made a couple samples of Y junctions to see if there was anything I could learn from them and sort of perfect the design of those Y junctions. So, and this is the one that I'm going to build for the primary pipes that has the 1.5 inch diameter on both sides going into 1 3/4. And then going down to the final Y, there's this Y and then another Y, and then they Y together. They're going to be coming in 1 3/4 inches. And so I made this pipe with the same angle as these, but this is now the 1 3/4 inch diameter right here at about 27 degrees of angle. And I stepped up this diameter now to a 2 inch because it was the next one available. That's, there's few choices to make. So this is how the system will now be built, is with these Y sections, and they will come in something like that or whatever. And the trick now is to show you how to to actually build these kind of Y sections. So let's go on to that next. Okay. Hi. Well, I'm now in the process of building one of these Y sections, and it's going to be for this one that has 1.5 inch diameter Ys coming in to an 1 3/4 inch collector. And what I did was I went and made, I believe it's called a miter box, but to me it's a cutting box. And all I did was took a couple pieces of 1/2 inch plywood and a board on the bottom, and I cut the board the distance of the diameter of the tube. In this particular case, it is 1 3/4 inches. So what I would do is I would lay the tube in here, and then when I clamp it shut, clamp it tight, it'll hold that tube in this box. And in this box, I have now cut a slot through which my saw can pass that is 26 degrees off of the inline or center line of the tubing, like that. So it's now 26 degrees. So I clamp the tube in there, put the saw through it, and cut it through, and that's how I get a 26-degree cut going through that tube. Now, this is the one for the 1 3/4 tubing. This is the one for the 1.5 inch tubing, and I have just cut the section that I need. So let me get this out of here. Now here is the pipe that you just saw me cut, and I was going to tack weld it together, and I thought, hey, well, you're hanging around here doing nothing, so might as well watch. So here is the piece again with that diagonal cut in it, and what I'm going to do is rotate one of these just around that way and then join them again like that. Okay, so let's see if I can do that with these gloves on. I'll put one of these really nice little magnetic triangles or arrows, whatever they are. Really handy things for this kind of work. Then I just bring them together as best I can. Let's slide this guy a little bit more. I like that. Okay. So now I'm going to tack the top side and then rotate it and get the underside. Nothing's much happening there. There, I think I got something going now. Love this. Dr. Flamo. Wonder why they called her that. Okay. There. Now, I'm going to come in and weld in the crack area. I mean, the bead area first. And okay, you've seen tack welding before, so I've tack welded the V on the one side. Now I've flipped it over and tacked it on the other side, and let's go on from there. And like that. Okay, now what I'm going to do is just clean this up, and then I will come back and show you how to decide where the cut should be across here that'll be just right for matching up on the lower part of the Y. So I'll see you in a few moments. Okay, now the piece has been cleaned up, and you can see what it looks like. And what I want to do is I want to be able to find out where to cut this to make this to the 1 3/4 inch pipe. And when I put this on here, it has a different shape, one from the other. And so I can't go directly and just draw a line here because this will be too small, because it does not come out to the edge everywhere. So the line must be some distance further up, but how to determine that? Well, it's actually pretty simple, because even though I can't use this as a determination for the circumference of the circle and where it's the same circumference around here, I can use a representation. So I've taken this piece of paper and I'm going to make a representation of the circumference of this tube, and that will be the paper. So I will now put some tape on it. Like that. And I want to put another piece of tape on just because it needs it. Like that. Okay, now this piece of paper is the same circumference as the tube. So now if I can slide the tube out from the paper like that, I now have a representation, and it's very nice and flexible. So what I do now is I take this nice flexible portion and I slide it right on until it's snug right up there, and it's lined up straight down. Here's this center line, and I want the center line to go down so it doesn't get cocked this way or that way. And that's right about where I want it. It's right about there. So then I take, let me get this just straight as can be. There we go. Now I'll hold this, my thumb right here. And right around that spot is right where I want to cut it. So I'm going to do that, and I shall return. See ya. Okay, I'm back from cutting it, and when I did so, it got cut like that, and I wound up with one of these little guys, which is absolutely useless. So I'll just toss that aside. And now here is where the two tubes are now going to be joining into one. And that's why one would not fit into the other except for the representation of the paper, because they are of different shapes. Now the trick is to get this shape to fit that. And that is very, very easy. I just simply put it in the vise. And let me slide you back here so that you can see that. Okay. Now let me see if... no, you can't. Okay, what I'm going to do is move you up. Hold on, grab onto something, and here we go. Okay, now you can see my vise sitting over there. And I put some soft jaws made from aluminum on there for protection. I don't want to put a crease in the tube. And then where it's welded together, I'm going to put that right on the side, just as a reference. Try to straighten it up as best I can, right there. Now I just sit and squeeze it like that, and then pull it back out. And now, see the shape that it's got? They look pretty similar, don't they? Okay, so now I do a test fitting on that, and this is why I wanted that center line, because it'll come right down through here, and I can see that I'm almost there. I just want to bring this down a little bit more, because there's a ledge right there. So I'll put this right back in here and just squeeze it a little more. I have now a cross section like that. And now look at that. I would say that's a pretty good fit, wouldn't you? So now I'm going to tack weld that, and I'll be back in just a moment. See ya. Okay, the final Y junction here has been tack welded together, and that's what it looks like. And then it's going to be cut off here so that it is a uniform length with this one. Just simply because it would be easier to make measurements if everything is similar. So these will be welded all up together when I get the rest of them made, but of course I'm going to need two more of the ones that go from 1.5 inches to 1 3/4. And when it comes to the larger guy, I'm going to need one more of these. So right now I'm going to turn my little garage here into a Y-junction factory and make the rest of those Y-junctions. And I'll see you next time. Oh, boy. Hi. Oh, how I hate to cut up my old custom headers. First set of headers I ever had. But they aren't timed, and I need a timed one, so these have got to go. But I need the flange and these little stubs to build a new one from. So I'm going to continue on with this amputation, and I'll see you next time. Well, here comes the beginning of the new growth from the amputation. Those are the first two tubes to be installed in the new exhaust system, and of course they're the ones, number 3 and number 5 in the center, that are already nice and synchronized at 180 degrees. So I'm going to bring them in right away on that, and the rest of it looks a bit like this, and I'll explain. Okay, now that I have established those two tubes coming down the center that are synchronized 180 degrees of rotation apart, which is correct for number 3 and 5 cylinders, I went ahead and then connected the final Y junction. That was the one that would connect the two primary Ys together, namely the one with 1 3/4 inch tubing down to 2 inch tubing, onto that preliminary Y coming from number 3 and 5. And then I connected the other primary Y onto the other end of that final Y in a vertical way to now give me a destination for the tube that leaves the stub flange and arrives at the other primary Y. And I'll then know how much and how to form those tubes to create that 7.5 inches of additional length. And this is what it looks like. Now it's ready to establish the other two tubes, which have to be lengthened to 7.5 inches. That is from there to here, and this one's going to loop down here and come in underneath. One of the ways that I am... Oh, incidentally, I'm leaving this brace in for where the Zeus fastener is, because this tells me where the fender is. And so this is an important reference. And I have lowered these tubes have stayed lower down here because this one has to cross in front of it, and I don't want to get it too close, of course, to a fiberglass fender. Now, the way that I'm establishing this one right here, and of course this one right here, is what I have done is I have taken the original 8 inches of length, added the 7.5, and made a 15.5 inch wire. And this is just regular coat hanger wire. And then I took into consideration what this length is right here, because these lengths, this 8 inch length goes all the way to the flange. So I reduced it by 2 inches, this length. So instead of 15.5 inches, it's now 13.5. And then I found out what the radius of the bends that I have in tubing are, and I tried to keep these radiuses to those bends. And then I have finally bent that wire to where the center line of this hole and the center line of that hole will look something like that. So that's the way I plan to build the tubing. So maybe the next time we get together, that'll be in place. And then again, maybe not. Who knows? We'll have to wait and see. So until next time. Okay, well, here it is Sunday morning, and I went and put this one branch going to number 7 cylinder in place, and I was on such a roll, I went up to number 1 cylinder and completed it also. So now this is the system as it is all just barely tacked together, and this is the one that ducks on down below. So let's just take a look at that one here. Okay, here comes number 1 cylinder, and I'm using up 7.5 inches of additional length before I finally come into this preliminary Y. The other part of that preliminary Y goes all the way over to number 7, utilizing that 7.5 inches of extra length also. And then here's the preliminary Y from the center 2 cylinders, and this one, and this is where they neck into the final Y that forms that train that will be coming out this exhaust system. So that's where I'm at next. So when we get together, maybe I'll have the completed tail section. So until next time. Okay, well, here is the section that is finished, at least on the driver's side. And that's what it looks like right there. And so now you can see that the 2 preliminary Ys are necked into the final Y, and then come down to this one section that has the full train running through it, and that of course would be this section right there. And then the opening right there exits out through the side of the front fender and extends out beyond the surface about an inch. Now on the Grand Prix ones that Lotus made, they put a megaphone into that last section, but I have decided not to do that because I really want to get that train going, and I want to come down that full tube, and then maybe later if I find out that the megaphone is better, then I might go into putting one in there. But for right now, that is the system as it is finally completed. And this would actually make a good street system also, exhaust system, with the exhaust pipe going to the muffler coming out of this last section that is right in here. Then you could just tape off of that, go back in the muffler, and close off this with a cap. And then when you want to become a weekend warrior at the drags, you just simply uncap that baby and off you go. So would you like to see how the whole system turned out for both drivers and passenger side after they're all metal sprayed and ready to go? Check this out. Here is that exhaust system that is now a timed exhaust system. And I would like to show you what it looks like on the passenger side. But first of all, notice that on the driver's side here, that the two cylinders in the middle are the shortest ones, and then the outer two have to make up this difference of 90 degrees of rotation of the crankshaft. Now let me show you what it looked like on the passenger side. Okay, this is what it looks like, and it is a bit different in shape because with the firing order on this side, it required that the two center cylinders be the longest and that the ones on the outside be the shortest. And so therefore you can see where the two outside cylinders race to get to this Y junction as quickly as possible. And then that distance is added to the distance that causes 90 degrees of rotation of the crankshaft and is added to the two center cylinders. And as you have seen, this one ducks under here and comes in on the lower Y, and this one loops right around this outside cylinder and comes right in on the upper Y. And that's what it looks like. So now, well, there you have it. That's a timed exhaust system, all set and ready to go set records of Bonneville. Now, if you needed any extra information on how to cut and form, I should say, the U-bends and the straight sections of the tubing, all that information can be found on the other Dr. Flamo tape of the crossed ram induction manifold. And so your requirements are probably going to vary from mine because you're working on a different car and you're going to have steering systems or brackets or front suspension systems or whatever. They're going to be in your way, so you're going to have to work it around in a different way. But if you follow the basic instructions in this tape, you will have a very efficient synchronized exhaust system that runs at peak performance at a particular RPM, which of course you choose. But even on the other sides, both higher and lower that RPM range, it's still going to be far more synchronized than an equal length exhaust system. So you're going to get the benefits of not only peak performance at the RPM that you want, but throughout most of the range, you're going to get increased efficiency, which means better gas mileage. So I hope you've enjoyed this Dr. Flamo tape. You might want to check out some of the others and see if there's something else you'll enjoy. And this is Dr. Flamo saying, until next time,